Close your eyes and let yourself drift as we embark on the most extraordinary journey imaginable, the complete story of everything that has ever existed, from the very first moment of time itself to the distant future that awaits us all. This is a story that spans nearly 14 billion years, a tale so vast and magnificent that it encompasses every star you've ever seen twinkling in the night sky, every grain of sand on every beach, every atom in your body, and every thought that has ever crossed your mind. In the beginning, there was nothing. But this nothing wasn't empty in the way we might imagine emptiness. It was a peculiar kind of nothing, a void pregnant with possibility, trembling with quantum uncertainty. Imagine, if you can, a state where the very concepts of space and time haven't yet emerged, where the laws of physics as we know them are still unwritten, waiting to spring into existence. This is where our story begins, in a realm so foreign to our everyday experience that even calling it a realm or saying it existed before the universe requires us to use words that don't quite fit, like trying to describe color to someone who has never seen. The quantum vacuum, as physicists call this primordial state, wasn't truly empty. It seethed with virtual particles, ghostly entities that popped into existence for periods of time so brief that they barely registered as existing at all before vanishing back into the void. These quantum fluctuations, these tiny ripples in the fabric of nothingness, were like whispers in an infinite library of silence, each one carrying the potential to become something more. Energy borrowed from nowhere, existing for moments measured in units so small that numbers lose their meaning, this was the canvas upon which reality would soon paint itself. Picture yourself floating in this pre-universe, though of course you couldn't really be there because there didn't exist yet. No up or down, no left or right, no yesterday or tomorrow. Just an endless, timeless potential, like the pause between heartbeats stretched out to infinity. The quantum foam, as some scientists poetically describe it, bubbled with possibilities. Each bubble represented a potential universe, most of them collapsing before they could become anything, like soap bubbles popping in slow motion, except there was no motion because time hadn't started its steady march. The fascinating thing about this pre-beginning state is that it might not have been unique to our universe. Some theories suggest that this quantum foam continuously spawns universes, each one a bubble that either collapses back into nothing or inflates into a full cosmos like ours. We might be just one success story among countless failed attempts, or perhaps one universe among infinite others, all existing in their own bubbles of spacetime, forever separated from each other by the very nature of existence itself. What triggered the transition from this quantum uncertainty to the birth of our universe? Scientists call it a quantum fluctuation, but that clinical term hardly captures the monumentous nature of what occurred. Imagine all the potential energy of an entire universe, compressed into a point smaller than the smallest subatomic particle we know of, smaller than a quark, smaller than anything we can meaningfully describe with words. This point, this singularity, contained within it all the energy that would ever exist, all the matter that would ever be, all the space that would ever expand, and all the time that would ever pass. The conditions in this primordial moment were so extreme that our physics equations break down trying to describe them. The temperature was infinite, or as close to infinite as anything can be. The density was beyond calculation. The four fundamental forces that govern our universe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were united as one superforce. Indistinguishable from each other in the extreme conditions of this cosmic seed. Think about the profound implications of this moment. Every star that would ever shine, every planet that would ever form, every living being that would ever draw breath, every thought that would ever be thought, all of it was contained in potential within this infinitesimal point. The carbon atoms in your body, the oxygen you're breathing right now, the calcium in your bones, the iron in your blood, all of these were present in potential, waiting to be forged in the hearts of stars that wouldn't exist for millions of years. This singularity wasn't sitting somewhere in empty space, waiting to explode. Space itself was contained within it. It wasn't ticking away moments before detonation because time itself was wrapped up inside it. The Big Bang, despite its name, wouldn't be an explosion in space but rather an explosion of space, a sudden and dramatic expansion of existence itself from this point of infinite density and temperature. The quantum mechanical nature of this beginning means that asking what caused it might be the wrong question entirely. In quantum mechanics, events can occur without classical causes, particles can tunnel through barriers they shouldn't be able to cross, and uncertainty isn't just a limitation of our knowledge but a fundamental feature of reality. The universe might have tunneled into existence from nothing, bootstrapping itself into being through processes that challenge our intuitive understanding of cause and effect. As we prepare to witness the birth of everything, consider how remarkable it is that we, collections of atoms forged in stellar furnaces, have developed the capability to piece together this story. We've built telescopes that can peer back through billions of years, particle accelerators that can recreate conditions from fractions of a second after the Big Bang, and mathematical frameworks that let us describe events that occurred before the Earth, the Sun, or even the first stars existed. We are the universe becoming conscious of itself, looking back at its own origins with wonder and curiosity. The stage is now set. The quantum fluctuation has occurred. The singularity is about to undergo the most dramatic transformation in the history of existence. In a moment shorter than any clock could measure, in a space smaller than any microscope could see, everything is about to begin. And then it happened. In a moment so brief that calling it a moment seems generous, the universe burst into existence. The Big Bang wasn't like a bomb exploding in empty space, it was space itself suddenly springing into existence and expanding at a rate that defies comprehension. The entire observable universe, everything we can see with our most powerful telescopes, every galaxy within our cosmic horizon, all of it was once compressed into a region smaller than a proton. And then, in less time than it takes light to cross that subatomic distance, it began to grow. The first unit of time that has any meaning in physics is called the Planck time, approximately 10 to the negative 43 seconds after the Big Bang. This is such a short period that if you were to divide a single second into as many Planck times as there have been seconds since the Big Bang, you would still have an incomprehensibly large number. During this Planck epoch, the universe was about 10 to the negative 35 meters across, the Planck length, and the temperature was about 10 to the 32 degrees Kelvin. These numbers are so extreme that they represent the boundaries of our physical theories. At these scales, quantum mechanics and general relativity collide in ways we don't yet fully understand. During this Planck epoch, all four fundamental forces were unified into a single superforce. Gravity, which seems so different from the other forces in our everyday experience, was indistinguishable from electromagnetism. The strong force that holds atomic nuclei together, and the weak force responsible for radioactive decay. The universe was a seething soup of pure energy, with particles and antiparticles constantly creating and annihilating each other in a cosmic dance of creation and destruction. As the universe aged to about 10 to the negative 36 seconds old, it underwent a phase transition that would shape everything that came after. Gravity separated from the other three forces, becoming its own distinct interaction. This was like water suddenly deciding to separate into hydrogen and oxygen, except far more fundamental. The universe was cooling as it expanded, dropping from those incomprehensible Planck temperatures to a merely unimaginable 10 to the 27 degrees Kelvin. Then came one of the most important events in cosmic history, inflation. Between 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of exponential expansion that dwarfs even the dramatic growth that started it all. During inflation, the universe increased in size by a factor of at least 10 to the 26, possibly much more. Every region of space doubled in size, then doubled again, then again, over and over, at least 90 times in that brief instant. To understand how dramatic this inflation was, imagine a grain of sand suddenly expanding to become larger than the entire observable universe today. That's the scale of expansion we're talking about, except it happened to the entire universe simultaneously. This wasn't matter flying apart through space, this was space itself stretching, carrying everything with it. The inflationary period solved several puzzles about our universe, explaining why it appears so uniform on large scales, why it's so geometrically flat, and why we don't see certain exotic particles that should have been produced in the early universe. The energy driving this inflation came from a field that permeated all of space, similar to how the Higgs field gives particles mass today. This inflating field, as it's called, was in an unstable state, like a ball perched on top of a hill. As it rolled down to a more stable configuration, it released enormous amounts of energy, driving the exponential expansion of space. When inflation ended, this energy was converted into particles, reheating the universe in a process called reheating, filling it with a hot, dense soup of fundamental particles. By 10 to the negative 12 seconds after the Big Bang, the universe had cooled to about 10 to the 15 degrees Kelvin, and another crucial transition occurred. The electroweak force, which had remained unified since gravity split off, separated into the electromagnetic force and the weak nuclear force. This gave us the four distinct forces we observe today. The Higgs field settled into its current state, giving mass to particles like the W and Z bosons that mediate the weak force, while leaving photons massless. The universe at this point was filled with a hot quark-gluon plasma, a state of matter so exotic that we can only recreate it for brief moments in our most powerful particle accelerators. Quarks, the building blocks of protons and neutrons, existed freely, not yet bound together. Gluons, the particles that carry the strong force, zipped between them. Electrons and their antimatter counterparts, positrons, were constantly being created and destroyed. Neutrinos, those ghostly particles that barely interact with matter, streamed through everything. As we reached 1 microsecond after the Big Bang, the universe had cooled to about 10 trillion degrees Kelvin. This might still seem incomprehensibly hot, but it was cool enough for a dramatic change. Quarks could no longer exist freely. The strong force pulled them together into composite particles, protons and neutrons, the building blocks of atomic nuclei. This phase transition, called the QCD phase transition, QCD stands for quantum chromodynamics, the theory of the strong force, fundamentally changed the nature of matter in the universe. For every billion quarks that combined into matter particles, there were 1,000,000,001 that combined into antimatter particles. When matter and antimatter meet, they annihilate each other, converting their mass entirely into energy according to Einstein's famous equation. As the universe continued to cool, this great annihilation played out on a cosmic scale. Billions upon billions of particles and antiparticles destroyed each other, filling the universe with high-energy photons. But that tiny asymmetry, that one extra matter particle for every billion matter-antimatter pairs, survived. Everything we see in the universe today, every star, planet, and living being, exists because of this minute imbalance. By 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Kelvin, still hotter than the center of our sun but cool enough for another crucial transition. Neutrinos, which had been constantly interacting with other particles, decoupled from the rest of matter. They began streaming freely through space, creating a cosmic neutrino background that still exists today, though it's incredibly difficult to detect. These primordial neutrinos carry information about the universe when it was only 1 second old, a fossil record of conditions in the infant cosmos. At this same moment, electrons and positrons were annihilating each other just as quarks and antiquarks had done earlier. The same mysterious asymmetry that saved matter from complete annihilation saved electrons too, leaving behind just enough to eventually form atoms. The universe was now dominated by photons, particles of light, with a smaller contribution from neutrinos, and an even smaller contribution from the matter particles that survived the Great Annihilation. Between 1 and 10 seconds after the Big Bang, the universe had cooled to about 1 billion degrees Kelvin, and the first atomic nuclei began to form. This process, called Big Bang nucleosynthesis, was the universe's first attempt at chemistry, though it was chemistry under conditions no laboratory could ever replicate. Protons and neutrons began sticking together, forming the nuclei of the lightest elements. The first and simplest nucleus to form was deuterium, also called heavy hydrogen, consisting of 1 proton and 1 neutron. But deuterium is fragile, easily broken apart by high-energy photons, and the universe was still so hot that most deuterium nuclei were destroyed almost as soon as they formed. This created a bottleneck in the formation of heavier elements, as deuterium is a necessary stepping stone to building more complex nuclei. As the universe continued to expand and cool, reaching about 100 million degrees Kelvin by the time it was a few minutes old, conditions finally became suitable for deuterium to survive. Once this bottleneck was passed, nuclear reactions proceeded rapidly. Deuterium nuclei combined with protons to form helium-3, or with other deuterium nuclei to form helium-4. Some traces of lithium-7 and beryllium-7 were also produced, but the universe was expanding and cooling too quickly for any heavier elements to form in significant quantities. By the time the universe was about 20 minutes old, Big Bang nucleosynthesis was essentially complete. The cosmic oven had cooled below the temperature needed for nuclear fusion. The universe's chemical composition was set, about 75% hydrogen nuclei, which are just single protons, 25% helium, for nuclei, and tiny traces of deuterium, helium-3, and lithium. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood, would have to wait for the first stars to forge them in their nuclear furnaces. But these weren't atoms yet, just naked nuclei. The universe was still far too hot for electrons to settle into stable orbits around nuclei. Instead, the universe was filled with a plasma, a soup of free nuclei and electrons, with photons constantly bouncing between them. Light couldn't travel far without hitting an electron and being scattered in a random direction. The universe was opaque, like being inside a glowing fog where you can see light all around but can't see through to distant objects. This plasma state would persist for hundreds of thousands of years. The universe continued expanding, continued cooling, but it was still too hot for atoms to form. Photons kept electrons and nuclei apart, like a cosmic game of keep-away played with particles. The universe was dominated by radiation during this era, the energy in photons exceeded the energy in matter. But as the universe expanded, the wavelengths of these photons stretched, reducing their energy. Eventually, matter would come to dominate, but that transition was still far in the future. During this time, the universe was remarkably smooth and uniform. The density varied by only about 1 part in 100,000 from place to place. But these tiny variations, these minute ripples in the density of matter and energy, would prove crucial. They were the seeds from which all structure in the universe would grow, the slight overdensities that would eventually collapse under gravity to form the first stars and galaxies. These density fluctuations had their origins in the quantum fluctuations during inflation, microscopic uncertainties blown up to cosmic scales. They created slight variations in temperature and pressure throughout the universe. In regions that were slightly denser, gravity was slightly stronger, pulling in more matter. In regions that were slightly less dense, matter would flow away toward the denser regions. But during this radiation-dominated era, the pressure from photons resisted gravitational collapse. Matter wanted to clump together, but radiation smoothed it out, creating acoustic oscillations, sound waves in the primordial plasma. These cosmic sound waves reverberated through the early universe, creating a pattern of compressions and rarefactions, like the peaks and troughs of waves on an ocean. The size of these waves was determined by the speed of sound in the plasma and the age of the universe, how far sound could travel before atoms formed and the waves froze in place. This pattern would later be imprinted on the cosmic microwave background and in the distribution of galaxies, a fossil record of sound waves from when the universe was young. Dark matter, that mysterious substance that doesn't interact with light, was also present during this time. In fact, there was about 5 times as much dark matter as ordinary matter. While ordinary matter was kept smooth by its interactions with radiation, dark matter could begin clumping under gravity. These dark matter clumps created gravitational wells that would later help ordinary matter collect more quickly once atoms formed. As we approach the end of this radiation-dominated era, the universe had expanded by a factor of about 1,000 since Big Bang nucleosynthesis ended. The temperature had dropped from billions of degrees to thousands of degrees. The stage was being set for one of the most important transitions in cosmic history, the formation of the first atoms and the release of light to travel freely through space for the first time. For nearly 400,000 years, the universe remained in this state of glowing plasma, a cosmic soup where light bounced endlessly between electrons and nuclei like a ball in a pinball machine. The temperature gradually dropped as space expanded, from millions of degrees to thousands, but it was still too hot for atoms to form. Every time an electron tried to settle into orbit around a nucleus, a high-energy photon would come along and knock it free again. The universe glowed with its own heat, but this light couldn't travel far. It was like being inside a star, light everywhere, but no transparency, no ability to see through the glowing gas to what lay beyond. But as the universe approached its 380,000th birthday, something remarkable was about to happen. The temperature had fallen to about 3,000 degrees Kelvin, roughly half the temperature of the Sun's surface. At this temperature, something crucial changed. Photons no longer had enough energy to consistently knock electrons away from nuclei. The cosmic pinball game was coming to an end. This transition didn't happen all at once across the entire universe. It was a gradual process that took place over thousands of years, but on cosmic timescales, it was relatively swift. Electrons began to settle into stable orbits around nuclei, forming the first true atoms. Hydrogen atoms formed first and in the greatest abundance, a single proton capturing a single electron. Helium atoms formed too, with their 2 protons, 2 neutrons, and 2 electrons. The traces of lithium nuclei that survived from Big Bang nucleosynthesis also captured their electrons. This era is called recombination, though that's something of a misnomer since electrons and nuclei had never been combined before. It's also called photon decoupling, which more accurately describes what happened. Photons, particles of light, decoupled from matter and began streaming freely through space. The universe, which had been opaque since its birth, suddenly became transparent. It was as if a cosmic fog had lifted, allowing light to travel unimpeded across the vastness of space. Imagine being in a steamy bathroom where the mirror and windows are completely fogged over, and then suddenly the steam condenses and the air clears. That's what happened to the entire universe during recombination. except instead of water vapor condensing into droplets, it was electrons condensing onto nuclei to form atoms. The universe went from being a glowing, opaque plasma to a transparent gas in a cosmic blink of an eye. The photons that were released during this transition have been traveling through space ever since. They've been stretched by the expansion of the universe, their wavelengths growing longer and their energy decreasing. What started as visible light, the orange glow of a universe at 3000 degrees, has been redshifted all the way into the microwave part of the spectrum. Today, we detect these ancient photons as the cosmic microwave background radiation, a faint glow coming from every direction in the sky with a temperature of just 2.7 degrees above absolute zero. This cosmic microwave background, or CMB as astronomers call it, is the oldest light we can see. It's a baby picture of the universe, showing us what it looked like when it was only 380,000 years old. The tiny temperature variations in the CMB, differences of just a few parts in 100,000, show us the seeds of structure, the slightly denser regions that would eventually grow into galaxies and galaxy clusters. With atoms formed and photons streaming freely, the universe entered what astronomers call the Dark Ages. This name might seem strange for an era that immediately followed the universe becoming transparent, but it's accurate. The universe was no longer glowing with its own heat, and the first stars hadn't yet formed to light up the darkness. The only light was the fading afterglow of the Big Bang, growing dimmer and redder as the universe expanded. During the Dark Ages, the universe was filled with a neutral gas of hydrogen and helium atoms, with trace amounts of lithium. This gas was almost perfectly uniform, varying in density by only tiny amounts. But gravity was at work, slowly but inexorably pulling matter toward the slightly denser regions. Dark matter, which had begun clumping earlier because it doesn't interact with light, had already formed a cosmic web of filaments and nodes. Ordinary matter began falling into the gravitational wells created by dark matter concentrations. The universe during this time was a much simpler place chemically than it is today. With only 3 elements, hydrogen, helium, and a tiny bit of lithium, there could be no complex chemistry, no molecules more complicated than molecular hydrogen, H2, and lithium hydride, LiH. The rich tapestry of elements that makes planets and life possible didn't yet exist. Carbon, oxygen, nitrogen, iron, all the elements that would become crucial to the story of the universe were waiting to be forged in stellar furnaces that hadn't yet ignited. As millions of years passed in darkness, gravity continued its patient work. The cosmic web became more pronounced, with matter flowing along dark matter filaments toward the nodes where filaments intersected. In the densest regions, the concentration of matter grew higher and higher. Clouds of hydrogen and helium gas collapsed under their own gravity, growing denser and hotter at their centers. The physics of this gravitational collapse is fascinating. As a gas cloud contracts, it heats up, gravitational potential energy is converted to kinetic energy, causing the particles to move faster. But for the collapse to continue, this heat needs to be radiated away. In the modern universe, heavy elements and molecules help clouds cool efficiently, but in the primordial universe, with only hydrogen and helium, cooling was much less efficient. This meant that only the most massive clouds could collapse, and they needed to be much more massive than star-forming clouds today. The first collapsing clouds were enormous, containing hundreds or thousands of times the mass of our Sun. As they contracted, they fragmented into smaller clumps, but even these fragments were huge by modern standards. The lack of heavy elements meant that the first generation of stars would be giants, massive beyond anything that forms in the universe today. In the hearts of these collapsing clouds, density and temperature climbed steadily. When the temperature at the core reached about 1000 degrees Kelvin, molecular hydrogen began to form in significant quantities. This was important because molecular hydrogen could radiate heat more efficiently than atomic hydrogen, allowing the clouds to cool and continue collapsing. But molecular hydrogen could only cool the gas to about 200 degrees Kelvin, much hotter than modern star-forming clouds that can cool to just 10 degrees above absolute zero. The collapse continued, with gravity pulling matter inward and pressure building at the center. When the core temperature reached about 2000 degrees Kelvin, the molecular hydrogen began to break apart again. This absorbed energy, temporarily slowing the collapse, but gravity was relentless. The density continued to increase, the temperature continued to rise. 10,000 degrees, 100,000 degrees, 1,000,000 degrees. Deep in the hearts of these primordial clouds, conditions were approaching those needed for nuclear fusion. The universe had been dark for millions of years, but that was about to change. The first stars were about to ignite, bringing light back to the cosmos and beginning the process of creating the elements that would make planets and life possible. The Dark Ages were coming to an end. The formation of these first stars wasn't uniform across the universe. In the densest nodes of the cosmic web, where dark matter and ordinary matter had accumulated the most, conditions for star formation were reached first. These regions would become the sites of the first galaxies. In less dense regions, star formation would come later or not at all. The universe was developing structure, transitioning from the smooth, uniform conditions after recombination to the complex, hierarchical structure we see today. As we stand on the threshold of the first stellar ignitions, it's worth pausing to consider how different the universe was at this moment compared to today. There were no galaxies as we know them, just diffuse clouds of gas falling into dark matter halos. There were no planets, no asteroids, no comets, the heavy elements needed to build solid objects didn't exist yet. The universe was chemically pristine, containing only the elements forged in the first few minutes after the Big Bang. Space itself was different too. The universe was smaller, denser, and hotter than today, even though it had already expanded tremendously since the Big Bang. The cosmic microwave background, which today has a temperature of 2.7 Kelvin, was warmer than, perhaps 20 or 30 degrees Kelvin when the first stars formed. This might not seem like much of a difference, but it meant that the universe had a higher minimum temperature. Today, gas clouds can cool to nearly absolute zero, but in the early universe, the cosmic microwave background provided a temperature floor below which gas couldn't cool. The stage was now set for one of the most transformative periods in cosmic history. The first stars were about to light up, ending the Dark Ages and beginning the era of cosmic dawn. These stellar pioneers would live fast and die young, but in their brief lives and spectacular deaths, they would forever change the universe, seeding it with the heavy elements that would make future generations of stars, planets, and life possible. In the depths of the cosmic Dark Age, approximately 100 million years after the Big Bang, the universe held its breath. The patient work of gravity had finally gathered enough material, compressed it sufficiently, heated it to the necessary temperatures. In the cores of the most massive gas clouds, in the densest nodes of the cosmic web, a critical threshold was about to be crossed. The temperature reached 10 million degrees Kelvin, and suddenly, nuclear fusion ignited. The first star in the universe had just been born. This first star was nothing like the stars we see today. It was a monster, perhaps 200 or 300 times the mass of our Sun, blazing with a luminosity millions of times greater than our parent star. Its surface temperature exceeded 100,000 degrees Kelvin, so hot that most of its light was emitted as ultraviolet radiation. If human eyes could have existed to see it, this star would have appeared blue-white, a brilliant beacon in the darkness that had shrouded the universe for so long. The nuclear fusion at this star's core was the same process that powers stars today, hydrogen nuclei combining to form helium, releasing energy in the process. But the conditions were extreme. The core temperature might have exceeded 100 million degrees Kelvin, 10 times hotter than the center of our Sun. The pressure was beyond imagination, with matter compressed to densities that dwarf anything we can create in laboratories. At these temperatures and pressures, nuclear fusion proceeded at a furious pace, consuming hydrogen fuel at a rate that would deplete even this massive star's reserves in just a few million years. As more and more of these massive first stars ignited across the universe, they began to transform their surroundings in profound ways. Their intense ultraviolet radiation ionized the neutral hydrogen gas around them, creating expanding bubbles of ionized gas like cosmic soap bubbles growing in the darkness. These ionization bubbles would eventually overlap and merge, beginning a process called reionization that would transform the entire universe from neutral gas back to ionized plasma, though much more diffuse than the plasma of the early universe. But the first star's most important contribution to cosmic evolution was their production of heavy elements. In their cores, temperatures and pressures were high enough not just to fuse hydrogen into helium, but to continue the fusion process further. Helium nuclei combined to form carbon. Carbon fused with helium to create oxygen. Oxygen fused with helium to produce neon, and with carbon to create silicon and sulfur. Step by step, element by element, these stellar furnaces were creating the periodic table. The process of element creation in these first stars was remarkably efficient. Their massive size meant they could build elements all the way up to iron, element 26 on the periodic table. Iron is special because it's the most stable nucleus. Fusing iron doesn't release energy but requires energy input. When a star's core becomes dominated by iron, fusion can no longer support it against gravity, and catastrophe follows. For the first stars, this catastrophe came quickly. After only 2 or 3 million years, a cosmic eye blink compared to our Sun's 10 billion-year lifetime, these massive stars had exhausted their nuclear fuel. When fusion stopped in their cores, there was nothing to hold back gravity. The core collapsed in less than a second, reaching densities comparable to atomic nuclei. Then it rebounded, sending a shock wave outward through the star. This shock wave, powered by a flood of neutrinos from the collapsing core, tore the star apart in a supernova explosion that briefly outshone an entire galaxy. These first supernovae were spectacular events that forever changed their regions of space. The explosion scattered the heavy elements forged in the star's core across thousands of light-years. Carbon, oxygen, nitrogen, silicon, sulfur, iron, elements that had never before existed in the universe were suddenly spread through space, enriching the surrounding gas clouds. Even more importantly, the extreme conditions during the supernova itself created elements heavier than iron. The intense flux of neutrons allowed rapid neutron capture, building elements like copper, zinc, silver, and gold. Some of the first stars might have met even more dramatic ends. The most massive ones, perhaps 500 times the mass of our Sun or more, might have collapsed directly into black holes without exploding. These direct collapse black holes would have been massive from birth, perhaps containing hundreds of solar masses. They might have been the seeds of the supermassive black holes we see at the centers of galaxies today, though this remains an active area of research and debate among astronomers. Other first stars might have exploded as parent-stability supernovae, a type of explosion that completely destroys the star, leaving no remnant behind. In these events, the core becomes so hot that photons spontaneously create electron-positron pairs, reducing the radiation pressure and triggering collapse. The resulting explosion is so powerful that it completely disrupts the star, scattering all of its material into space. These explosions would have been visible across the observable universe, the ultimate fireworks displays of the early cosmos. As millions of years passed, more and more first stars formed, lived their brief lives, and died in spectacular fashion. Each death enriched the universe a little more with heavy elements. The pristine hydrogen and helium gas of the early universe was gradually becoming contaminated with heavier elements, what astronomers call metals, even though many of these elements aren't metals in the chemical sense. This metal enrichment had profound effects on subsequent star formation. Heavy elements are much more efficient at radiating heat than hydrogen and helium. This meant that gas clouds enriched with even tiny amounts of heavy elements could cool more effectively, allowing them to fragment into smaller clumps. The second generation of stars could therefore be much less massive than the first generation. While the first stars were all giants, the second generation included stars more like our Sun, stars that could live for billions rather than millions of years. The first galaxies were beginning to assemble during this era. They weren't the grand spiral and elliptical galaxies we see today, but rather small, irregular collections of stars, perhaps containing only millions of stars rather than the hundreds of billions in modern galaxies. These proto-galaxies formed in the densest dark matter halos, where gas could accumulate most efficiently. As stars formed and died within them, they gradually built up their content of heavy elements. The process of reionization continued as more stars formed. Each hot, massive star created an expanding bubble of ionized gas around itself. These bubbles grew and merged, creating an increasingly complex topology of ionized and neutral regions. The universe began to resemble Swiss cheese, with bubbles of ionized gas as the holes and neutral gas as the cheese. The pattern of reionization wasn't uniform across the universe. In regions where galaxies were forming most actively, reionization proceeded quickly. In cosmic voids, where matter density was low and star formation was rare, neutral gas persisted longer. This created a complex, three-dimensional structure to reionization, with ionized regions growing and connecting like a cosmic network spreading through space. The ultraviolet photons from these early stars and galaxies didn't just ionize hydrogen, they also had profound effects on the formation of subsequent generations of stars and galaxies. The ionizing radiation heated the gas it encountered, raising its temperature and pressure. This made it harder for small dark matter halos to capture and retain gas. Only halos above a certain mass threshold could overcome this heating and continue forming stars. This feedback mechanism helped regulate star formation in the early universe, preventing it from proceeding too rapidly and exhausting all available gas at once. As the universe aged through its first billion years, the rate of star formation steadily increased. More and more dark matter halos grew massive enough to form galaxies. These early galaxies were sites of intense star formation, converting gas into stars at rates that would seem phenomenal by today's standards. Some of these early galaxies were forming hundreds or even thousands of new stars per year, compared to the 1 or 2 stars per year that form in our Milky Way today. The early galaxies were also beginning to develop structure. While they started as irregular blobs of stars and gas, gravitational interactions and rotational motion began organizing them. Some developed disk-like structures that would eventually evolve into spiral galaxies. Others remained more spheroidal, the predecessors of elliptical galaxies. The diversity of galaxy types we see today had its origins in these early formative processes. Black holes were playing an increasingly important role in galaxy evolution. As matter fell into the black holes at galaxy centers, it formed accretion disks, swirling maelstrom of gas heated to millions of degrees. These accretion disks emitted intense radiation across the electromagnetic spectrum, from radio waves to X-rays. When the black holes were actively feeding, they could outshine all the stars in their host galaxies combined, creating what we call active galactic nuclei or quasars. The radiation and jets from these active black holes had profound effects on their surroundings. They could heat gas throughout their host galaxies, shutting down star formation. They could blow gas completely out of smaller galaxies, regulating their growth. This feedback from black holes helped establish the relationships we see today between black hole mass and galaxy properties, a cosmic symphony where black holes and galaxies evolved together in harmony. Meanwhile, the cosmic web was becoming more defined. Dark matter and ordinary matter continued flowing along filaments toward nodes. Where filaments intersected, galaxy clusters began forming, collections of hundreds or thousands of galaxies bound together by gravity. These clusters would eventually become the largest gravitationally bound structures in the universe, containing quadrillions of solar masses of material. The chemical evolution of the universe continued apace. Each generation of stars further enriched the cosmos with heavy elements. By the time the universe was 1 billion years old, some regions had already achieved metal abundances 1/10 that of our Sun. This might not sound like much, but it represented an enormous change from the pristine hydrogen and helium of the early universe. Different elements were produced by different processes, creating a complex chemical evolution. Massive stars produced lots of oxygen and other alpha elements, elements built from helium nuclei, or alpha particles. Less massive stars, when they eventually evolved into red giants and planetary nebulae, produced lots of carbon and nitrogen. Type Ia supernovae, explosions of white dwarf stars in binary systems, which required time to develop, produced much of the universe's iron and neighboring elements on the periodic table. The abundance patterns of different elements became cosmic clocks and tracers, allowing astronomers to piece together the history of star formation and chemical enrichment. By studying the chemical compositions of stars and gas clouds, we can determine when they formed and what types of stars contributed to their enrichment. It's like cosmic archaeology, using element abundances as artifacts to reconstruct the past. As reionization neared completion around 1 billion years after the Big Bang, the universe had been fundamentally transformed from its dark age state. Instead of a uniform sea of neutral gas, space was filled with a complex ecosystem of galaxies, stars, black holes, and ionized gas. The cosmic web had developed into a vast network of filaments and voids, with galaxies strung along the filaments like lights on cosmic Christmas tree strands. The end of reionization marked another major transition in cosmic history. With the universe fully reionized, ultraviolet light could travel freely through space without being absorbed by neutral hydrogen. This made the universe transparent to ultraviolet radiation for the first time since recombination, though at a much lower density than the early plasma phase. Galaxies could now see each other across vast distances, their light traveling unimpeded through the ionized intergalactic medium. This newly transparent universe allowed for new types of interactions between galaxies. Ultraviolet radiation from star-forming galaxies could influence gas in neighboring galaxies. Galactic winds, driven by supernovae and stellar winds, could blow metal-enriched gas out of galaxies and into intergalactic space, enriching even the vast spaces between galaxies with heavy elements. The stage was now set for the universe to enter what we might call its adolescence. The wild star formation of the early universe would gradually settle into a more regulated process. Galaxies would grow through both continued star formation and mergers with other galaxies. The cosmic web would continue to evolve, with matter flowing along filaments and accumulating in clusters. And somewhere, in some galaxy, on some planet that didn't yet exist, the elements forged in these early stars would eventually come together to create life and consciousness, allowing the universe to contemplate its own origins. As the universe entered its second billion years, a grand architectural project was underway on the largest scales imaginable. The cosmic web, that vast network of dark matter and gas that spans the entire observable universe, was becoming increasingly defined and structured. Like a master architect working with invisible scaffolding, gravity was organizing matter into a breathtaking pattern of filaments, walls, nodes, and voids that would define the large-scale structure of the cosmos for billions of years to come. The cosmic web is one of the most magnificent structures in nature, though its full grandeur only becomes apparent when we look at the universe on scales of millions of light-years. Imagine a three-dimensional spider web the size of the observable universe, but instead of silk strands, the filaments are made of dark matter and gas, with galaxies embedded along them like dewdrops on a morning web. The nodes where filaments meet are the sites of galaxy clusters, the most massive gravitationally bound structures in the universe. Between the filaments lie vast cosmic voids, regions of space that contain very little matter, some spanning hundreds of millions of light-years across. This cosmic architecture didn't arise randomly but emerged from those tiny quantum fluctuations in the early universe that were amplified during inflation. The slightly denser regions had a gravitational advantage, pulling in surrounding matter. The slightly less dense regions lost matter to their denser neighbors, becoming ever emptier. Over billions of years, this process transformed near uniformity into the complex structure we observe today. Dark matter played the leading role in forming this cosmic web. Making up about 85% of all matter in the universe, dark matter doesn't interact with light or ordinary matter except through gravity. This allowed it to begin clumping earlier than ordinary matter, creating the gravitational scaffolding that ordinary matter would later follow. Dark matter halos, invisible concentrations of dark matter, became the sites where galaxies would form, like invisible molds shaping visible matter. The formation of galaxies within this cosmic web was a complex dance of physics. Gas flowed along dark matter filaments, cooling and condensing in the deepest gravitational wells. When the gas density became high enough, stars began forming, transforming diffuse gas clouds into the luminous galaxies we observe. But this wasn't a simple, one-way process. The energy released by star formation and supernovae pushed back against infalling gas, creating a feedback loop that regulated galaxy growth. Early galaxies grew through two main processes: steady gas accretion and dramatic mergers. Gas accretion was like a cosmic rain, with cool gas continuously falling into galaxies along filaments, providing fresh fuel for star formation. This process could sustain star formation for billions of years, allowing galaxies to grow steadily larger and more massive. Mergers, on the other hand, were violent events that could completely transform galaxies in just a few 100 million years. When two galaxies collided, their stars almost never collided directly. Space is so vast that stars passed by each other like ships in the night. But the gas in the galaxies collided violently, triggering intense bursts of star formation. The gravitational forces during mergers could completely reshape galaxies, turning orderly spiral disks into chaotic elliptical galaxies. The first major galaxy mergers were spectacular events. Two small proto-galaxies, each perhaps containing only billions of stars, would spiral toward each other along a dark matter filament. As they approached, tidal forces would distort their shapes, pulling out long streams of stars and gas called tidal tails. When the galaxies finally merged, the collision would trigger a starburst, forming hundreds of new stars per year in a brilliant but brief cosmic fireworks display. These early mergers were crucial for building up the massive galaxies we see today. Our own Milky Way, with its hundreds of billions of stars, was built through dozens of mergers over cosmic time. Each merger added mass and angular momentum, gradually building the grand spiral structure we inhabit today. The process continues even now, the Milky Way is currently absorbing several small dwarf galaxies, and in about 4 billion years, it will merge with our neighbor, the Andromeda Galaxy. As galaxies grew larger and more numerous, they began to form groups and clusters. Galaxy groups, containing a few to a few dozen galaxies, formed first in the smaller dark matter halos. These groups were bound together by gravity but were still fairly loosely organized, with galaxies orbiting around their common center of mass at relatively leisurely speeds of a few hundred kilometers per second. Galaxy clusters were altogether different beasts. Forming at the nodes where multiple filaments of the cosmic web intersected, clusters could contain hundreds or thousands of galaxies, all bound together in a gravitational embrace. The galaxies in clusters orbited at tremendous speeds, sometimes exceeding 1,000 kilometers per second. The space between galaxies in clusters wasn't empty but filled with extremely hot gas, heated to tens of millions of degrees by the cluster's gravitational field. This intercluster medium, as astronomers call it, is one of the most extreme environments in the universe. The gas is so hot that it emits X-rays, making galaxy clusters some of the brightest X-ray sources in the sky. The gas is also extremely diffuse, with densities so low that it would be considered a perfect vacuum by laboratory standards. Yet there's so much of this gas that it contains more ordinary matter than all the galaxies in the cluster combined. The formation of a galaxy cluster was a process that unfolded over billions of years. It began with a particularly dense region of the cosmic web, where multiple filaments converged. Galaxies and galaxy groups fell in along these filaments, accelerating as they descended into the cluster's gravitational well. As they fell, they were stripped of their gas by ram pressure from the intracluster medium, like wind stripping leaves from a tree. This process, called ram pressure stripping, could completely shut down star formation in infalling galaxies, transforming blue, star-forming spiral galaxies into red, dead elliptical galaxies. The galaxies that fell into clusters early in cosmic history experienced a particularly violent process called galaxy harassment. The repeated gravitational interactions with other cluster galaxies and the cluster's tidal field gradually transformed their morphologies, turning spirals into ellipticals and disrupting smaller galaxies entirely. The centers of galaxy clusters became cosmic graveyards, filled with elliptical galaxies that had long ago exhausted their gas and ceased forming new stars. But clusters weren't just sites of galaxy death, they were also laboratories for exotic physics. The extreme conditions in clusters allowed processes that couldn't occur elsewhere. Cosmic rays, charged particles accelerated to nearly the speed of light, were produced in abundance by shock waves in the intracluster medium. These cosmic rays interacted with magnetic fields that permeated the cluster, creating diffuse radio emission that astronomers can observe today. The dark matter in galaxy clusters revealed itself through gravitational lensing. The immense mass of a cluster, most of it dark matter, bent spacetime around it, causing light from more distant galaxies to bend as it passed by. This created distorted, magnified images of background galaxies, sometimes stretching them into long arcs or even complete rings called Einstein rings. By studying these distortions, astronomers could map the distribution of dark matter in clusters, revealing the invisible scaffolding that held these massive structures together. Meanwhile, in the vast cosmic voids between filaments, a very different story was unfolding. These voids, some spanning hundreds of millions of light-years, contained very little matter. The few galaxies that did form in voids evolved in relative isolation, without the interactions and mergers that shaped galaxies in denser regions. Void galaxies tended to be smaller and less evolved, cosmic hermits that had lived quiet lives away from the hustle and bustle of filaments and clusters. The voids weren't completely empty, though. They contained a diffuse gas, even more rarefied than the intracluster medium. They also contained dark energy, that mysterious force that would eventually come to dominate the universe's expansion. In the early universe, dark energy's effects were negligible compared to matter and radiation, but as the universe expanded and matter diluted, dark energy's constant density meant it would eventually take over. The cosmic web continued to evolve as the universe aged. Matter flowed from voids to filaments, from filaments to clusters. The rich got richer while the poor got poorer in a cosmic example of hierarchical structure formation. Computer simulations of this process, requiring millions of hours of supercomputer time, show the cosmic web evolving like a living thing, with filaments growing and merging, voids expanding, and clusters assembling at the nodes. This large-scale structure of the universe encoded information about fundamental physics. The size of the largest structures told us about the horizon scale during inflation. The abundance of clusters revealed the amount of dark matter and dark energy. The pattern of galaxies on the sky contained information about the quantum fluctuations that seeded all structure. The cosmic web was like a vast physics experiment, testing our theories on scales no laboratory could ever achieve. As the universe approached its 5 billionth birthday, the cosmic web had developed into something approaching its modern form. The largest galaxy clusters contained thousands of galaxies and weighed quadrillions of solar masses. The longest filaments stretched for hundreds of millions of light-years. The largest voids had expanded to encompass volumes that could contain thousands of Milky Way-sized galaxies, if only there was matter there to form them. While the universe was organizing itself on the grandest scales, an equally important story was unfolding on much smaller scales, within the hearts of stars. Each star was a nuclear furnace, transforming lighter elements into heavier ones through fusion reactions that released the energy making stars shine. This cosmic alchemy, playing out in billions of stars across billions of years, gradually enriched the universe with the full periodic table of elements, transforming the chemically pristine early cosmos into the element-rich universe we inhabit today. The second generation of stars, formed from gas slightly enriched by the first stellar generation, were markedly different from their predecessors. With even trace amounts of heavy elements to help cool the gas, these stars could form at much lower masses. While the first stars were all giants, dozens or hundreds of times more massive than our Sun, the second generation included stars across a wide range of masses. From red dwarfs less than a tenth the mass of our Sun to blue giants dozens of times more massive. This diversity of stellar masses was crucial because different mass stars live very different lives and die very different deaths, each contributing unique elements to the cosmic mixture. Low-mass stars, those less than about 8 times the mass of our Sun, live long, relatively peaceful lives. The smallest red dwarfs can shine steadily for trillions of years, far longer than the current age of the universe. These cosmic misers fuse hydrogen so slowly that they'll still be shining long after stars like our Sun have died. Stars like our Sun, with masses between about 0.8 and 8 times solar mass, live for millions to billions of years. They spend most of their lives fusing hydrogen into helium in their cores, maintaining a stable balance between gravity pulling inward and radiation pressure pushing outward. But when the hydrogen in their cores is exhausted, their story becomes more interesting. The core contracts and heats up while the outer layers expand and cool, transforming the star into a red giant. In the red giant phase, these medium-mass stars become element factories. The core becomes hot enough to fuse helium into carbon through the triple alpha process, 3 helium nuclei combining almost simultaneously. This process requires very precise conditions because beryllium-8, the intermediate step, is incredibly unstable and decays in about 10 to the negative 16 seconds. Only at temperatures above 100 million degrees Kelvin do enough beryllium-8 nuclei exist at any moment for a third helium to occasionally collide with one before it decays. Once carbon is formed, it can capture another helium nucleus to form oxygen. In stars massive enough, the process continues with neon, magnesium, and silicon being formed. But stars like our Sun can't generate the core temperatures needed to fuse elements heavier than oxygen. Instead, they develop a different element-making process in their outer layers. As these stars age into the asymptotic giant branch phase, they experience thermal pulses, periodic helium flashes that dredge up material from deep inside the star to the surface. Between these pulses, the star can capture neutrons onto iron seed nuclei, building heavier elements through what's called the slow neutron capture process, or S process. This process creates about half of all elements heavier than iron, including strontium, barium, and lead. The S process is called slow because neutron captures happen rarely enough that if an unstable nucleus is created, it usually has time to beta decay, converting a neutron to a proton, before capturing another neutron. This means the S process follows a very specific path through the periodic table, creating particular isotopes of heavy elements. It's a patient process, taking thousands of years to build up heavy elements atom by atom. Eventually, these medium-mass stars shed their outer layers in stellar winds, creating beautiful planetary nebulae, glowing shells of gas illuminated by the hot stellar core left behind. These planetary nebulae, despite their name having nothing to do with planets, return much of the star's mass to interstellar space, now enriched with carbon, nitrogen, oxygen, and S-process elements. The stellar core, exposed after the outer layers are shed, becomes a white dwarf, a dense stellar cinder about the size of Earth but containing about half the mass of the Sun. White dwarfs themselves can become element factories under the right conditions. If a white dwarf has a companion star and can steal matter from it, it can accumulate material on its surface. When enough material accumulates, it can trigger a thermonuclear explosion, a type Ia supernova. These explosions are particularly important for cosmic chemistry because they produce most of the universe's iron peak elements, iron, nickel, cobalt, and neighboring elements on the periodic table. Type Ia supernovae are remarkably uniform in their brightness, making them excellent standard candles for measuring cosmic distances. But they're also crucial for chemical evolution. Each explosion converts about half a solar mass of carbon and oxygen into iron peak elements, scattering them across thousands of light-years. These explosions can occur billions of years after the original star formed, providing a delayed injection of iron into the cosmic element mixture. High-mass stars, those more than 8 times the mass of our Sun, live fast and die young. The most massive stars burn through their nuclear fuel in just a few million years, racing through successive fusion stages. After exhausting hydrogen in their cores, they fuse helium to carbon and oxygen. Then carbon fusing produces neon, sodium, and magnesium. Neon fusion creates oxygen and magnesium. Oxygen fusion produces silicon, sulfur, argon, and calcium. Finally, silicon fusion creates iron and nickel. Each successive fusion stage happens faster than the last. A 20 solar mass star might spend 10 million years fusing hydrogen, 1 million years fusing helium, 1,000 years fusing carbon, 1 year fusing neon, 6 months fusing oxygen, and just 1 day fusing silicon. The star's interior develops an onion-like structure, with shells of different elements undergoing fusion around an iron core. When the iron core grows to about 1.4 times the mass of our Sun, the Chandrasekhar limit, catastrophe strikes. Iron fusion doesn't release energy but absorbs it. With no energy source to support it, the core collapses in less than a second, reaching nuclear density. The collapse is halted by neutron degeneracy pressure and the strong nuclear force, causing the core to rebound. This rebound, combined with a flood of neutrinos from the forming neutron star, drives a shock wave through the star. As this shock wave propagates outward, it heats the stellar material to billions of degrees, triggering explosive nucleosynthesis. In these extreme conditions, a rich variety of elements are created. The shock wave provides the energy needed to create elements heavier than iron through rapid neutron capture, the R process. Unlike the slow S process in dying low-mass stars, the R process happens in seconds, with neutron captures occurring faster than beta decay. This allows the R process to create very neutron-rich isotopes that then decay to stable heavy elements. The R process creates about half of all elements heavier than iron, including gold, platinum, uranium, and thorium. For decades, astronomers debated where exactly the R process occurred, in supernovae or elsewhere. Recent observations have shown that while supernovae contribute some R process elements, the merger of neutron stars is likely responsible for most of the universe's gold and other heavy R process elements. Core collapse supernovae scatter these newly forged elements across interstellar space with tremendous force. The explosion can accelerate material to speeds exceeding 10,000 km per second, creating expanding supernova remnants that plow through the interstellar medium. These remnants stay hot and visible for thousands of years, glowing in X-rays as the shocked gas slowly cools. The most massive stars, those above about 25 solar masses, might collapse directly into black holes without exploding. These failed supernovae swallow most of the elements the star created during its lifetime, removing them from the cosmic recycling system. But even these stars contribute to element enrichment through their powerful stellar winds, which blow off their outer layers during their lives. Some massive stars experience parinstability supernovae, where the core becomes so hot that photons spontaneously create electron-positron pairs. This removes pressure support, triggering a collapse that leads to complete disruption of the star. These explosions are so powerful that they leave no remnant behind, no neutron star or black hole, and scatter all of the star's material into space. They produce huge amounts of radioactive nickel-56, which decays to cobalt-56 and then iron-56, making these supernovae exceptionally bright and long-lasting. As generations of stars lived and died, each contributed its unique mixture of elements to the interstellar medium. Low-mass stars provided carbon, nitrogen, and S-process elements. Type Ia supernovae delivered iron peak elements. Massive star winds and supernovae contributed oxygen, neon, magnesium, silicon, sulfur, and R-process elements. The interstellar medium became an ever-richer soup of elements, each new generation of stars forming from material more enriched than the last. This process of chemical enrichment wasn't uniform across galaxies. Star-forming regions became enriched first, while gas in galactic halos remained more pristine. Galactic winds, driven by the combined effect of many supernovae, could blow metal-enriched gas out of galaxies entirely, enriching the intergalactic medium. Conversely, galaxies could acquire fresh, low-metallicity gas through accretion from the cosmic web, diluting their metal content. The metallicity of a star, astronomers confusingly call all elements heavier than helium metals, became a cosmic clock. By measuring the metal content of stars, we can determine when they formed. The oldest stars in our galaxy have metallicities less than 1,000th that of the Sun, formed when the universe was less than 1 billion years old. The Sun itself, with its relatively high metallicity, could only have formed after billions of years of chemical enrichment. Different elements peaked at different times in cosmic history. Oxygen, produced efficiently by massive stars, built up quickly. Iron took longer to accumulate, requiring the evolution of lower-mass stars into Type Ia supernova progenitors. Elements like gold and uranium, produced primarily in rare neutron star mergers, built up most slowly. The chemical evolution of the universe is written in the element abundances we observe in stars, gas clouds, and galaxies. About 9 billion years after the Big Bang, in an unremarkable spiral arm of an ordinary galaxy, conditions were finally right for something extraordinary to happen. The universe had matured sufficiently that its chemical composition could support not just new stars, but also the formation of rocky planets, complex chemistry, and eventually, life itself. This is the story of how our particular corner of the cosmos came to be, the formation of our Sun, our solar system, and the remarkable planet we call home. The Milky Way galaxy, our cosmic home, had already lived through billions of years of evolution by this time. It had grown through mergers with smaller galaxies, developing its characteristic spiral structure with a central bulge, a flat disk, and spiral arms where density waves triggered ongoing star formation. The galaxy had settled into a relatively stable middle age, forming new stars at a steady rate of a few per year, recycling gas through stellar birth and death in a sustainable cosmic ecosystem. Our story begins in a giant molecular cloud, a vast assemblage of gas and dust perhaps 50 light-years across and containing thousands of times the mass of our Sun. These molecular clouds are stellar nurseries, the birthplaces of stars and planetary systems. This particular cloud, located about 26,000 light-years from the galactic center, was composed primarily of hydrogen and helium, but crucially, it also contained about 2% heavier elements. Carbon, oxygen, silicon, iron, and traces of every natural element up to uranium. Something disturbed this cloud about 4.6 billion years ago. Perhaps it was the shock wave from a nearby supernova, or maybe the cloud simply reached a critical density through its own slow contraction. Whatever the trigger, parts of the cloud began to collapse under their own gravity. The cloud fragmented into hundreds of smaller cores, each destined to become a star or stellar system. One of these cores, containing perhaps twice the mass of our current Sun, would become our solar system. As this solar nebula collapsed, it began to rotate faster, like a figure skater pulling in their arms. The rotation prevented collapse perpendicular to the rotation axis, causing the cloud to flatten into a disk. Most of the mass concentrated in the center, forming a protostar that would become our Sun. The remaining few percent of the mass formed a protoplanetary disk around the young star, a cosmic pizza of gas and dust from which planets would eventually form. The temperature in this disk varied dramatically with distance from the forming Sun close to the center. Temperatures exceeded 1000 degrees Kelvin, hot enough to vaporize even rocky materials. Farther out, temperatures dropped below the freezing point of water, then below the freezing points of methane and ammonia. This temperature gradient would prove crucial in determining the composition of planets at different distances from the Sun. Within this disk, tiny dust grains began sticking together through electrostatic forces, like dust bunnies forming under your bed. These microscopic particles grew to millimeter-sized, then centimeter-sized aggregates. This early growth phase was relatively gentle, with particles sticking together when they collided at low speeds. But growing from centimeter-sized pebbles to kilometer-sized planetesimals was more challenging, the meter-size barrier, as planetary scientists call it. Objects of about a meter in size faced a problem. They were too large to be held up by gas drag but too small for gravity to be significant. They tended to collide at speeds that shattered them rather than allowing growth. How planetesimals overcame this barrier remains debated, but one possibility is that they grew rapidly through gravitational instabilities in dense regions of the disk, essentially skipping the problematic meter-size range. Once planetesimals reached sizes of a few kilometers, their own gravity became significant. They could attract and capture smaller objects, growing through a process called runaway accretion. The largest planetesimals in each region grew fastest, quickly dominating their neighborhoods. Within just a few 100,000 years, these planetary embryos had grown to sizes of thousands of kilometers, Moon or Mars-sized objects. In the inner solar system, where temperatures were high, only rocky and metallic materials could condense into solid form. The planetesimals here were made of iron, nickel, silicon, magnesium, and other rock-forming elements. Water and other volatile compounds remained as vapor, eventually being blown away by the young sun's stellar wind. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds, dense and compact. The formation of Earth itself was a violent process lasting about 100 million years. It began as one planetary embryo among many in the inner solar system. Through a series of collisions and mergers with other embryos and countless smaller planetesimals, it grew to nearly its current size. Each major impact added mass and energy, keeping the young Earth in a partially molten state. Heavy elements like iron sank toward the center, while lighter rocky materials floated to the surface, differentiating the planet into a metallic core and rocky mantle. The most dramatic event in Earth's early history was the moon-forming impact, occurring perhaps 50 million years after Earth began forming. A Mars-sized planetary embryo, often called Theia, collided with the young Earth at an oblique angle. The impact was catastrophic, vaporizing much of both bodies and launching debris into orbit around Earth. This debris, primarily from the mantles of both bodies, coalesced to form the Moon within just a few thousand years. This giant impact theory explains many peculiarities of the Earth-Moon system, including the Moon's lack of iron and the similar isotopic compositions of Earth and Moon rocks. Beyond the asteroid belt, in the outer solar system, conditions were very different. Temperatures were low enough for water, methane, and ammonia to freeze into solid ice. Planetesimals here could grow much larger because they had more material to work with, both rock and ice. The largest of these icy planetesimals grew massive enough to capture hydrogen and helium gas directly from the solar nebula, becoming the gas giant planets. Jupiter formed first and fastest, reaching its current mass of 300 Earth masses within just a few million years. Its formation had profound effects on the rest of the solar system. Jupiter's massive gravity stirred up nearby planetesimals, preventing them from coalescing into a planet. This is why we have an asteroid belt rather than another planet between Mars and Jupiter. Jupiter also acted as a barrier, preventing material from the outer solar system from drifting inward, helping to keep the inner solar system relatively dry. Saturn formed slightly later and grew more slowly, reaching about 100 Earth masses. Its formation might have been slowed by Jupiter, which competed for the same reservoir of gas and planetesimals. The spectacular ring system that makes Saturn so distinctive today wouldn't form until much later, possibly from the destruction of an icy moon or comet that ventured too close to the planet. Uranus and Neptune, the ice giants, formed even later and farther from the Sun. With less gas available at their distances and forming after much of the nebular gas had dissipated, they couldn't grow as large as Jupiter and Saturn. They're composed primarily of water, methane, and ammonia ices, with smaller hydrogen and helium envelopes. Their formation might have taken 10 million years or more, and they might not have formed at their current locations. Indeed, the early solar system was a much more chaotic place than the orderly system we see today. Planetary migration was common, with gravitational interactions between planets and the remaining disk material causing orbits to shift. Jupiter likely migrated inward and then back outward, a journey that would have dramatically affected the asteroid belt and inner planets. Neptune might have formed closer to the Sun than Uranus and then swapped positions during a period of dynamical instability. This instability, sometimes called the Late Heavy Bombardment, occurred perhaps 700 million years after the Solar System formed. As the giant planets settled into their final orbits, they scattered billions of comets and asteroids throughout the Solar System. Many of these impacted the inner planets, creating the heavily cratered surfaces we see on the Moon, Mercury, and Mars. Earth was similarly bombarded, though erosion and plate tectonics have erased most evidence of these ancient impacts. During this chaotic era, Earth was developing the conditions necessary for life. The planet had cooled enough for water vapor to condense into oceans. The atmosphere, initially composed of hydrogen and helium captured from the solar nebula, had been replaced by volcanic gases, water vapor, carbon dioxide, nitrogen, and sulfur compounds. This secondary atmosphere would be transformed over billions of years. First by chemical processes and later by life itself. The delivery of water and organic compounds to Earth remains a topic of active research. While some water was likely present in the original building blocks of Earth, much might have been delivered later by comets and asteroids, especially during the Late Heavy Bombardment. These impacts also delivered organic molecules, the carbon-based compounds that would become the building blocks of life. Meanwhile, the Sun had settled into its main sequence phase, fusing hydrogen steadily in its core. The young Sun was actually about 30% dimmer than it is today, which presents a puzzle known as the faint young Sun paradox. With less solar energy, Earth should have been frozen solid, yet geological evidence shows liquid water existed on the surface. The solution likely involves a stronger greenhouse effect from higher concentrations of carbon dioxide and possibly methane in the early atmosphere. The outer regions of the Solar System were populated with billions of icy bodies that never grew large enough to become planets. The Kuiper Belt, extending from Neptune's orbit to about 50 astronomical units from the Sun, contains hundreds of thousands of objects larger than 100 kilometers across. Even farther out, the Oort cloud, a spherical shell of comets extending perhaps halfway to the nearest star, contains trillions of icy bodies, remnants from the Solar System's formation. As our Solar System settled into a stable configuration about 4 billion years ago, it had developed a remarkable diversity of worlds. Rocky planets with metal cores and potential for geological activity in the inner system. Gas and ice giants with complex moon systems in the outer system. A belt of rocky asteroids and multiple regions of icy comets. Each world was unique, shaped by its particular history of formation, impacts, and evolution. On a young planet orbiting an ordinary star, something extraordinary was about to happen. The universe, after 10 billion years of stellar evolution and element forging, had finally produced a world with just the right conditions for chemistry to become biology, for matter to organize itself into forms that could grow, reproduce, and evolve. Earth, barely 500 million years old and still cooling from its violent formation, was about to become the stage for the most complex phenomenon we know of in the universe, life. The early Earth was a world that would seem alien to us today. The atmosphere contained virtually no free oxygen, instead being rich in nitrogen, carbon dioxide, water vapor, and possibly methane and ammonia. Volcanic activity was intense, with lava flows and ash clouds constantly reshaping the surface. Meteorite impacts, though less frequent than during the Late Heavy Bombardment, still occurred regularly, delivering both destruction and valuable organic compounds from space. The oceans that covered most of Earth's surface were not the blue expanses we know today. They were likely greenish or brown, rich in dissolved iron and other minerals leached from newly formed rocks. The Moon loomed much larger in the sky, orbiting far closer to Earth than it does today, causing massive tides that swept across the shallow seas twice daily with tremendous force. A day lasted only about 6 hours, as the Earth spun much faster than its current 24-hour rotation. In this seemingly hostile environment, chemistry was becoming increasingly complex. The Miller-Urey experiment in the 1950s showed that simple organic molecules, amino acids, the building blocks of proteins, could form spontaneously when electric sparks passed through a mixture of gases thought to resemble Earth's early atmosphere. Lightning strikes, ultraviolet radiation from the sun, and the energy from meteorite impacts could all have driven similar reactions on the early Earth. But creating simple organic molecules is one thing, assembling them into living systems is quite another. Life requires not just complex molecules but organized systems capable of metabolism, growth, reproduction, and evolution. How this transition from chemistry to biology occurred remains one of the great mysteries in science, but we have some compelling clues and hypotheses. One possibility is that life began in deep-sea hydrothermal vents, where superheated water rich in minerals erupts from the ocean floor. These environments provide a constant source of chemical energy and create gradients in temperature and pH that could drive the formation of complex molecules. The mineral surfaces at these vents could have served as catalysts, speeding up chemical reactions and providing templates for organizing organic molecules. Another hypothesis places the origin of life in warm little ponds, as Charles Darwin once speculated. These shallow bodies of water could have concentrated organic molecules through cycles of evaporation and refilling. Clay minerals at the bottom of such ponds might have provided surfaces for organizing and protecting delicate organic molecules from destruction. Recently, scientists have proposed that life might have originated in terrestrial hot springs, environments that exist where volcanic activity heats groundwater. These springs go through wet-dry cycles that could concentrate molecules and drive the formation of polymers, long chains of simpler molecules. The hot spring environment also provides a variety of minerals and chemical conditions that could support diverse prebiotic chemistry. Wherever life began, it faced a fundamental challenge: how to store and transmit information. Modern life uses DNA for information storage, RNA for information transfer, and proteins for most cellular functions. But DNA is too complex and stable to have arisen spontaneously, while proteins can't replicate themselves. This chicken and egg problem led to the RNA world hypothesis, the idea that early life was based on RNA, which can both store information and catalyze chemical reactions. In this RNA world, self-replicating RNA molecules would have been the first true living entities. These molecular replicators would have competed for resources, with more efficient replicators becoming more common over time, the beginning of evolution by natural selection. Eventually, these RNA-based organisms would have developed the ability to synthesize proteins, which are more versatile catalysts than RNA. Later still, DNA would have taken over the role of information storage, being more stable than RNA. The first living cells were probably simple bags of molecules surrounded by lipid membranes, similar to soap bubbles but far more sophisticated. These protocells had to solve several challenges: maintaining their internal chemistry different from their surroundings, obtaining energy and raw materials from their environment, and reproducing by dividing into daughter cells. The earliest cells were likely prokaryotes, lacking a nucleus and other membrane-bound organelles that characterize more complex cells. These early organisms were probably chemotrophs, obtaining energy by catalyzing chemical reactions rather than from sunlight. They might have fed on the organic molecules that had accumulated in the oceans, the primordial soup. But this food source was limited and non-renewable. Life needed to find a more sustainable energy source, and it found it in the sun. Photosynthesis, the process of capturing light energy to drive chemical reactions, evolved relatively early in life's history, perhaps 3.5 billion years ago. The first photosynthetic organisms probably used hydrogen sulfide or other compounds as electron donors, not producing oxygen as a byproduct. But around 2.5 billion years ago, cyanobacteria evolved oxygenic photosynthesis, using water as an electron donor and releasing oxygen as waste. This innovation would transform the planet. For the first time, life was producing free oxygen, a highly reactive gas that had been virtually absent from Earth's atmosphere. At first, this oxygen was absorbed by dissolved iron in the oceans, creating banded iron formations, layers of rust that we can still see in ancient rocks today. But once the oceans were oxidized, oxygen began accumulating in the atmosphere in what's known as the Great Oxidation Event. The rise of oxygen was catastrophic for most existing life forms, which had evolved in an oxygen-free world. Oxygen is toxic to many biological molecules, causing what we now call oxidative stress. The Great Oxidation Event was likely the first mass extinction in Earth's history, killing off countless species of anaerobic organisms. But it also created new opportunities. Oxygen respiration is far more efficient than anaerobic metabolism, providing much more energy from the same amount of food. Life responded to the oxygen crisis with remarkable innovation. Some organisms retreated to oxygen-free environments, deep mud, hot springs, and animal guts, where their anaerobic descendants still thrive today. Others evolved mechanisms to tolerate or even use oxygen. Most remarkably, some cells engulfed oxygen-using bacteria, forming a symbiotic relationship that would give rise to mitochondria, the powerhouses of complex cells. This event, the evolution of eukaryotic cells with mitochondria, was one of the most important transitions in life's history. It occurred perhaps 1.8 billion years ago when an archaean cell, a type of prokaryote, engulfed a bacterium but didn't digest it. Instead, the two formed a partnership. The bacterium provided efficient energy production through oxygen respiration, while the host cell provided protection and nutrients. Over time, the bacterium evolved into the mitochondrion, losing its independence but gaining a permanent home. A similar event gave rise to chloroplasts, the organelles that perform photosynthesis in plants and algae. A eukaryotic cell already containing mitochondria engulfed a cyanobacterium, which evolved into the chloroplast. This serial endosymbiosis, as it's called, created cells with multiple energy-generating systems, setting the stage for the evolution of complex multicellular life. For over 1 billion years after eukaryotes evolved, life remained mostly single-celled. But around 1.5 billion years ago, some eukaryotes began experimenting with multicellularity. At first, these were probably just colonies of identical cells sticking together. But over time, cells within these colonies began to specialize, taking on different roles, some for feeding, others for reproduction, still others for protection. The advantages of multicellularity were numerous. Larger organisms could access new food sources, avoid being eaten by single-celled predators, and develop more complex behaviors. But multicellularity also required sophisticated coordination between cells, including mechanisms for cells to communicate, differentiate into different types, and even die for the good of the organism, programmed cell death, or apoptosis. By 600 million years ago, complex multicellular life had evolved in the oceans. The Ediacaran fauna, named after the Ediacara Hills in Australia where fossils were first found, included a variety of soft-bodied organisms unlike anything alive today. Some were frond-like, others disc-shaped or quilted. These creatures were probably early experiments in animal body plans, most of which would prove evolutionary dead ends. Then, about 541 million years ago, life experienced an unprecedented burst of innovation known as the Cambrian explosion. Within just a few million years, a blink of an eye in geological terms, most major animal body plans appeared in the fossil record. Arthropods with jointed legs and external skeletons. Mollusks with shells. Chordates with primitive backbones. Echinoderms with five-fold symmetry. It was as if nature was trying out every possible way to build an animal. The Cambrian explosion might have been triggered by rising oxygen levels, which finally reached concentrations that could support large, active animals. The evolution of eyes might have accelerated evolution by creating new predator-prey relationships. The development of hard parts, shells, carapaces, and skeletons, not only provided protection but also left far better fossils, which might make the explosion seem more sudden than it really was. Life was also transforming the planet in other ways. Plants and algae were pulling carbon dioxide from the atmosphere and sequestering it in their tissues and in sediments when they died. This biological carbon pump helped regulate Earth's climate, preventing a runaway greenhouse effect like what happened on Venus. The roots of early land plants, which first appeared around 450 million years ago, accelerated the weathering of rocks, further drawing down atmospheric CO2. The colonization of land was another major transition in life's history. The first land organisms were probably microbial mats and simple plants similar to modern mosses. These pioneers had to evolve protection against desiccation, mechanisms to obtain water and nutrients without being immersed in them, and structures to support themselves against gravity without the buoyancy of water. Plants evolved vascular systems to transport water and nutrients, structural tissues like wood to grow tall, and seeds to protect and nourish their offspring. Animals followed plants onto land, first arthropods like millipedes and spiders, then vertebrates evolving from lobe-finned fish. Each group had to solve the challenges of terrestrial life, breathing air, preventing water loss, supporting their weight, and reproducing without water. By 350 million years ago, vast forests of ferns, horsetails, and early trees covered the continents. These carboniferous forests were so productive that they pulled enormous amounts of CO2 from the atmosphere, cooling the planet and sequestering carbon in vast coal deposits that we still mine today. Insects evolved flight, becoming the first animals to take to the air. Amphibians gave rise to reptiles, which evolved the amniotic egg, a private pond that allowed them to reproduce fully on land. The Permian-Triassic extinction 252 million years ago, the largest mass extinction in Earth's history, killed over 90% of marine species and 70% of terrestrial vertebrates. It might have been caused by massive volcanic eruptions in Siberia that released huge amounts of CO2 and toxic gases. But life, as always, recovered and diversified. The extinction cleared ecological niches that were filled by new groups, including the dinosaurs. Dinosaurs dominated terrestrial ecosystems for over 160 million years, evolving into a stunning variety of forms. Some grew to enormous sizes. The long-necked sauropods were the largest land animals ever. Others evolved feathers and took to the air, giving rise to birds. Marine reptiles like ichthyosaurs and plesiosaurs ruled the oceans. Pterosaurs, the first vertebrates to evolve powered flight, filled the skies. During the age of dinosaurs, flowering plants evolved and diversified in partnership with pollinating insects. This coevolution produced the incredible diversity of flowers we see today, each adapted to attract specific pollinators. Mammals also appeared during this time, but remained small and mostly nocturnal, living in the shadows of the dinosaurs. The asteroid impact 66 million years ago that ended the age of dinosaurs created another opportunity for life to reinvent itself. Mammals, freed from dinosaur competition, rapidly diversified into forms filling every ecological niche: grazers, predators, flyers, swimmers, and eventually primates with large brains and grasping hands. The evolution of humans represents another threshold in cosmic complexity. For the first time, matter had organized itself into forms capable of abstract thought, language, and culture. Humans could pass information not just through genes but through teaching and learning. We developed technology that extended our capabilities far beyond our biological limits. In just the past few thousand years, an instant in cosmic time, humans have transformed the planet. We've altered the atmosphere, modified the genetics of other organisms, and even left the planet to explore space. We've developed the ability to understand our own origins, to trace the story of the universe from the Big Bang to the present. As we arrive at the present moment in our cosmic journey, we find ourselves in a universe that has aged 13.8 billion years since its dramatic beginning. The cosmos today is vastly different from its hot, dense origins. It has expanded by a factor of over a billion, cooled to just 2.7 degrees above absolute zero, and developed structure on every conceivable scale from subatomic particles to galactic superclusters spanning hundreds of millions of light-years. This is our universe now, a cosmos in what we might call its middle age, still vibrant with activity but showing signs of the long, slow changes that will define its future. The universe today is dominated by dark energy, that mysterious force that causes the expansion of space itself to accelerate. Dark energy makes up about 68% of the total energy density of the universe. Dark matter comprises about 27%, and ordinary matter, everything we can see and touch, every star, planet, and atom, makes up just 5%. We live in a universe where the familiar is the exception, where most of existence consists of substances we don't fully understand. Galaxies continue to form stars, but at a much slower rate than in the universe's youth. The peak of cosmic star formation occurred about 10 billion years ago when the universe was just 3.8 billion years old. Back then, the average star formation rate across the universe was about 10 times higher than today. Now, galaxies are more settled, more mature. They've used up much of their gas or blown it away through stellar winds and supernovae. Star formation continues, but it's a shadow of what it once was. Our own Milky Way galaxy exemplifies this cosmic middle age. It forms about 1 to 2 new stars per year, a modest rate that could continue for billions of years with its current gas reserves. The galaxy contains roughly 400 billion stars, ranging from tiny red dwarfs that will shine for trillions of years to massive blue giants that will explode as supernovae within millions of years. Between the stars lies the interstellar medium, a complex ecosystem of gas and dust, magnetic fields and cosmic rays, where new stars are slowly gestating. The Milky Way isn't alone in its cosmic neighborhood. It's part of the Local Group, a collection of over 80 galaxies bound together by gravity. Our largest neighbor, the Andromeda Galaxy, lies 2.5 million light-years away and is currently approaching us at about 110 kilometers per second. In approximately 4.5 billion years, the Milky Way and Andromeda will collide and merge, creating a giant elliptical galaxy that some astronomers have already named Milkomeda. Throughout the observable universe, we can see billions of galaxies, each one an island universe containing billions or even trillions of stars. These galaxies come in a stunning variety of forms. Spiral galaxies like our own, with their elegant pinwheel structures and ongoing star formation. Elliptical galaxies, massive spheroidal collections of old stars with little gas or current star formation. Irregular galaxies, often distorted by gravitational interactions with neighbors. Dwarf galaxies, containing just millions of stars but far outnumbering their larger cousins. Many galaxies host supermassive black holes at their centers, monsters containing millions or billions of times the mass of our Sun. Our own galaxy's central black hole, Sagittarius A*, weighs about 4 million solar masses. These black holes can dramatically affect their host galaxies when they're actively feeding. As matter spirals into them, it forms an accretion disk that can shine brighter than all the galaxy's stars combined, creating what we call active galactic nuclei or quasars. The most distant quasars we observe show us galaxies as they were over 13 billion years ago, when the universe was less than a billion years old. Their light has been traveling through space for almost the entire history of the universe, stretched by cosmic expansion from visible light into infrared. These ancient beacons allow us to study how galaxies and black holes evolved in the early universe. Between galaxies stretches the intergalactic medium, a sparse web of gas that contains more ordinary matter than all the galaxies combined. This gas is incredibly diffuse, typically just 1 atom per cubic meter, but it fills such an enormous volume that its total mass is substantial. The gas is kept hot, millions of degrees in galaxy clusters, by the gravitational energy released as matter falls into the cosmic web's gravitational wells. The cosmic web itself continues to evolve, though more slowly than in the universe's youth. Matter flows along dark matter filaments toward nodes, where galaxy clusters grow ever more massive. The largest structures in the universe, these clusters can contain thousands of galaxies, quadrillions of solar masses of dark matter, and gas heated to tens of millions of degrees that glows in X-rays. Dark matter remains one of the universe's greatest mysteries. We can see its gravitational effects everywhere, in the rotation of galaxies, the motions of galaxy clusters, the bending of light through gravitational lensing, and the large-scale structure of the universe. Yet we still don't know what it is. Experiments deep underground search for weakly interacting massive particles, WIMPs. Space telescopes look for the gamma rays that might be produced when dark matter particles annihilate, and particle accelerators try to create dark matter in high-energy collisions. So far, dark matter has kept its secrets. Even more mysterious is dark energy, the force causing the universe's expansion to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy appears to be a property of space itself, a cosmic anti-gravity that grows stronger as the universe expands and space becomes more abundant. The simplest explanation is Einstein's cosmological constant, a fixed energy density of empty space, but other possibilities include dynamic fields that change over time or modifications to general relativity on cosmic scales. The acceleration of cosmic expansion has profound implications. Galaxies that aren't gravitationally bound to us are receding at ever-increasing speeds. Eventually, they'll be moving away faster than light, which is possible because it's space itself expanding, not motion through space. When this happens, their light will no longer be able to reach us. The observable universe is shrinking, not in actual size but in the number of galaxies we can see. Trillions of years from now, only our local group of galaxies will remain visible. But that far future is still unimaginably distant. Today, the universe teems with activity. New stars are still forming, though at a declining rate. In stellar nurseries like the Orion Nebula, we can watch the birth process unfold, dense cores collapsing. Protostars gathering material from surrounding disks, stellar winds clearing away the natal gas to reveal young star clusters. These newborn stars are often surrounded by protoplanetary disks where planets are forming right now, just as our solar system formed 4.6 billion years ago. Planets, we now know, are abundant in the universe. The Kepler Space Telescope and other planet-hunting missions have discovered thousands of exoplanets orbiting other stars. These discoveries have revealed an astonishing diversity of planetary systems. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, super-Earths with no analog in our solar system. Planets orbiting binary stars, like the fictional Tatooine from Star Wars. Rogue planets wandering through interstellar space without a parent star. Based on these observations, astronomers estimate that there are more planets than stars in our galaxy, hundreds of billions of worlds. Many of these planets orbit within their star's habitable zone, where liquid water could exist on the surface. The discovery of potentially habitable exoplanets has intensified the search for life beyond Earth, one of the most profound questions facing science today. Life on Earth continues to evolve and adapt, now under the influence of human activity. We've entered what some scientists call the Anthropocene, a new geological epoch defined by human impact on the planet. We're causing the sixth mass extinction, altering the climate through greenhouse gas emissions, and modifying the genetics of organisms through biotechnology. Yet life, as it has throughout its history, continues to surprise us with its resilience and adaptability. The search for life elsewhere in the universe has intensified with improved technology. We search for biosignatures in the atmospheres of exoplanets, looking for gases like oxygen and methane that might indicate biological processes. We listen for radio signals from alien civilizations through programs like SETI. We explore our own solar system, finding environments that might harbor life, the subsurface ocean of Europa, the methane lakes of Titan, the ancient river valleys of Mars. The universe today is also a laboratory for extreme physics. Neutron stars, the collapsed cores of massive stars, pack more than the Sun's mass into a sphere just 20 kilometers across. Their density is so extreme that a teaspoon of neutron star material would weigh as much as Mount Everest. These objects spin at incredible rates, some rotating hundreds of times per second, creating lighthouse beams of radiation we observe as pulsars. When neutron stars collide, they create events so violent that they shake the fabric of spacetime itself, generating gravitational waves that we can now detect with instruments like LIGO and Virgo. The first neutron star merger detected in both gravitational waves and light, GW 170817, confirmed that these collisions are where many heavy elements like gold and platinum are forged. We are literally made of star stuff, including elements created in some of the most violent events in the universe. Black holes continue to fascinate and mystify us. We've now directly imaged the event horizons of supermassive black holes in M87 and our own galactic center, seeing the glowing accretion disks that surround these cosmic monsters. Stellar mass black holes, formed from the collapse of massive stars, occasionally reveal themselves when they feed on companion stars, creating X-ray binaries that flicker and flare as matter spirals to its doom. The cosmic microwave background, that ancient light from when the universe was only 380,000 years old, continues to provide insights into cosmology. Precise measurements by satellites like Planck have mapped tiny temperature variations across the sky, revealing the seeds of cosmic structure and constraining the universe's age, composition, and geometry with unprecedented precision. These observations confirm that the universe is geometrically flat to within measurement error and provide evidence for inflation in the early universe. Yet for all we've learned, mysteries abound. What is dark matter? What is dark energy? How did life begin? Are we alone in the universe? What lies beyond the observable universe? What happened before the Big Bang, if before even has meaning? These questions drive continuing research and observation, pushing the boundaries of human knowledge. Technology continues to advance our understanding. The James Webb Space Telescope peers deeper into space and time than ever before, seeing the first galaxies forming in the early universe. Gravitational wave observatories open an entirely new window on the cosmos, allowing us to hear the universe through ripples in spacetime. Neutrino detectors capture ghostly particles from the Sun, supernovae, and even the Big Bang itself. Particle accelerators like the Large Hadron Collider recreate conditions from fractions of a second after the Big Bang, studying the fundamental forces and particles that govern all matter and energy. Quantum computers promise to simulate complex systems that are beyond classical computation, potentially unlocking secrets of black holes, the early universe, and the nature of spacetime itself. As we lift our gaze from the present and peer into the cosmic future, we enter a realm where the timescales become so vast that they challenge human comprehension. The universe has existed for 13.8 billion years, but this is merely its infancy. The story of the cosmos will continue for trillions upon trillions of years, a future so extended that our entire history so far will seem like a brief flash at dawn before an almost eternal day. Let us journey forward through time and witness the slow transformation of everything we know. In the near future, cosmically speaking, our sun will continue its steady brightening. Every billion years, it increases in luminosity by about 10% as helium accumulates in its core, making fusion reactions more intense. In about 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate more rapidly than they do today. The increased water vapor in the atmosphere will create a stronger greenhouse effect, raising temperatures further in a runaway feedback loop. As temperatures rise, carbon dioxide will be drawn out of the atmosphere by increased weathering of rocks, but this will eventually reduce CO2 levels so much that photosynthesis becomes impossible. The last plants will die roughly 500 to 600 million years from now, and with them will go most animal life that depends on oxygen and the food chain that plants support. Some microbial life might persist for another billion years, hiding in deep rocks or near hydrothermal vents, but the Earth's surface will become increasingly hostile to life as we know it. About 1.75 billion years from now, the Moon, which has been slowly spiraling away from Earth at about 3.8 centimeters per year, will be far enough away that total solar eclipses will no longer be possible. The Moon will appear too small to completely cover the Sun's disk. This might seem like a minor change, but it marks the end of one of nature's most spectacular phenomena, one that has inspired humans throughout history. In approximately 4.5 billion years, our local group will witness a cosmic collision of epic proportions. The Andromeda Galaxy, currently approaching us, will finally reach the Milky Way. The collision won't be like a car crash. The vast distances between stars mean that direct stellar collisions will be extremely rare. Instead, the two galaxies will pass through each other, their gravitational fields distorting each other's shapes, pulling out long tidal streams of stars. Over the course of several 100 million years, the two galaxies will orbit around their common center of mass, passing through each other multiple times before eventually merging into a single, giant elliptical galaxy. The night sky during this merger will be spectacular, with the distorted shape of Andromeda filling much of the sky, new star formation triggered by the collision creating brilliant stellar nurseries, and tidal streams of stars creating new patterns in the heavens. Our solar system will likely survive this galactic merger, though it might be flung into a different orbit around the new galactic center or even ejected into intergalactic space. If Earth somehow still harbored observers, they would witness the night sky transforming over millions of years, familiar constellations scattered and reformed, the band of the Milky Way replaced by the more uniform glow of an elliptical galaxy. Around 5 billion years from now, our Sun will begin its death throes. Having exhausted the hydrogen in its core, it will begin fusing hydrogen in a shell around an inert helium core. This will cause the Sun to expand dramatically, becoming a red giant star. Its surface will cool to about 3000 Kelvin, giving it a reddish color, but its enormous size will make it far more luminous than today. The expanding sun will engulf Mercury, then Venus. Earth's fate is uncertain. The sun will lose mass as it expands, causing Earth's orbit to spiral outward, but tidal forces might cause Earth to spiral inward faster. Either way, Earth will be rendered completely uninhabitable, its surface temperature exceeding 1000 degrees Celsius, hot enough to melt rock. The oceans will have long since boiled away, the atmosphere stripped off by the intense solar wind. The sun's red giant phase will last about 1 billion years, during which it will experience thermal pulses as helium fusion occasionally ignites in its core. Eventually, the sun will shed its outer layers, creating a planetary nebula, a beautiful shell of glowing gas expanding into space. The sun's core, exposed and compressed to about the size of Earth but containing half the sun's original mass, will become a white dwarf, slowly cooling over trillions of years. As we look further into the future, star formation across the universe will continue but at an ever-declining rate. The universe is using up its supply of hydrogen gas, converting it into helium and heavier elements locked inside stars and stellar remnants. By about 100 billion years from now, most galaxies will have exhausted their gas reserves. Star formation will slow to a trickle, with new stars forming only occasionally from gas released by dying stars or collected from the intergalactic medium. The universe will enter what's called the degenerate era, lasting from about 10 to the power of 14 years, 100 trillion years, to 10 to the power of 40 years in the future. During this incomprehensibly long period, the universe will be dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The last low-mass red dwarf stars, which can shine for trillions of years, will finally exhaust their fuel and fade away. The universe will become a dark place, lit only by the occasional collision of stellar remnants or accretion onto black holes. White dwarfs will slowly cool, their internal heat radiating away into space. After about 10 to the power of 15 years, they'll cool to the same temperature as the cosmic microwave background, becoming black dwarfs, cold, dark spheres of degenerate matter. These black dwarfs might occasionally collide, creating supernovae that briefly light up the darkness, but such events will be extraordinarily rare. Even protons, which we consider stable, might decay over these vast timescales. If proton decay occurs, and this is still uncertain, it would happen on a timescale of at least 10 to the power of 34 years. All ordinary matter would gradually dissolve into lighter particles, positrons, electrons, neutrinos, and photons. White dwarfs and neutron stars would slowly evaporate, their constituent particles decaying away. Black holes will become the longest-lived objects in the universe. But even they aren't eternal. Through a quantum mechanical process discovered by Stephen Hawking, black holes slowly evaporate by emitting radiation. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter and evaporate faster. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. Supermassive black holes, millions or billions of times more massive, would last even longer, up to 10 to the power of 100 years. As a black hole evaporates, it gets smaller and hotter, radiating faster and faster until it finally explodes in a burst of energy, returning all its mass to the universe as radiation. During the black hole era, from about 10 to the power of 40 to 10 to the power of 100 years in the future, black holes will be the only remaining sources of energy in the universe. Matter falling into them will create the last sources of light. When black holes finally evaporate, they'll briefly illuminate the darkness with their death throes, but then even these will fade. After the last black hole evaporates, the universe will enter the dark era, a time when only leptons, electrons and positrons, and photons remain. The universe will have reached maximum entropy, a state of complete disorder where no more energy can be extracted to do work. The temperature everywhere will be the same, just slightly above absolute zero. No structures, no complexity, no possibility for life or consciousness as we understand it. Yet even in this seemingly dead universe, quantum fluctuations will continue. Given enough time, and time is one thing the universe will have in abundance, these fluctuations could potentially create new structures. Some physicists have speculated about Boltzmann brains, conscious entities that could spontaneously arise from random fluctuations. The probability of such an event is infinitesimally small, but in an infinite future, even the improbable becomes inevitable. The ultimate fate of the universe depends on the nature of dark energy. If dark energy is truly a cosmological constant, the universe will expand forever, growing ever colder and more dilute. But if dark energy changes over time, other fates are possible. It could decay, allowing gravity to eventually halt and reverse the expansion, leading to a big crunch where the universe collapses back to a singularity. Or it could grow stronger, leading to a big rip where the expansion becomes so violent that it tears apart all structures, from galaxy clusters down to atoms and even subatomic particles. Recent observations suggest that the heat-death scenario, eternal expansion and cooling, is most likely. The universe will become an increasingly empty, cold, and dark place. The distances between galaxy clusters will grow so vast that each cluster will become causally disconnected from all others, unable to communicate or interact. Each will become its own island universe, slowly fading to black. This might seem like a depressing end to our cosmic story, but consider what the universe will have accomplished. From a hot, dense, simple beginning, it will have given rise to incredible complexity, galaxies, stars, planets, life, and consciousness. The universe will have experienced beauty, love, curiosity, and wonder through the conscious beings it created. It will have come to know itself, if only briefly on cosmic timescales. And perhaps this isn't the end of the story. Some theories suggest our universe might be one of many in a multiverse, with new universes constantly being born. Our universe's death might coincide with or contribute to the birth of new universes, carrying on the cycle of cosmic evolution. The information and complexity developed in our universe might somehow seed or influence these new cosmic offspring. Others speculate about the possibility of intelligent life engineering its own survival, perhaps by creating new universes, manipulating dark energy, or transcending physical reality altogether. Given billions of years of technological development, what might conscious beings achieve? Could they find ways to harvest energy from black holes, reverse entropy locally, or even escape to other universes? As we near the end of our cosmic journey, we must acknowledge that the story we've told, while based on our best current understanding, is far from complete. The universe guards its deepest secrets jealously, and for every question we've answered, new mysteries have emerged. There are alternative possibilities for how the universe began, what it's made of, and where it's heading. There are phenomena we observe but can't explain, patterns we see but don't understand, and theoretical possibilities that challenge our basic assumptions about reality itself. One of the most profound mysteries is the question of what, if anything, came before the Big Bang. The standard model of cosmology treats the Big Bang as the beginning of time itself, making the question of before meaningless. But this might be too simplistic. Several theories suggest our Big Bang might have been one event in a larger, possibly eternal process. The cyclic universe model proposes that the universe undergoes endless cycles of expansion and contraction. In this scenario, our Big Bang was actually a big bounce, the rebound from a previous universe that contracted to a very small size but didn't quite reach a singularity. Each cycle might last trillions of years, with the universe expanding, cooling, and eventually contracting again under its own gravity. Dark energy complicates this picture, but some versions of the theory suggest dark energy might decay over vast timescales, allowing eventual recollapse. Another possibility is eternal inflation, where our universe is just one bubble in an infinite multiverse. In this model, inflation never completely ends but continues forever in some regions of a larger spacetime. Occasionally, inflation ends locally, creating bubble universes like ours. These bubbles would be causally disconnected, unable to communicate with each other, each potentially having different physical laws and constants. Our universe might be one of infinite bubbles, constantly being created in an eternal inflationary multiverse. String theory, one of the leading candidates for a theory of quantum gravity, suggests even stranger possibilities. In string theory, the fundamental constituents of reality aren't point particles but tiny vibrating strings of energy. These strings vibrate in different patterns, and each pattern corresponds to a different particle, an electron, a quark, a photon. But for the mathematics to work out, string theory requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension we experience. These extra dimensions might be compactified, rolled up so small that we can't detect them directly. Imagine an ant walking on a garden hose. From far away, the hose looks one-dimensional, just a line. But up close, the ant can walk around the circumference as well as along the length. Similarly, our universe might have 6 or 7 extra dimensions curled up at every point in space, too small for us to notice but affecting physics at the quantum scale. The shape and size of these extra dimensions would determine the physical laws and constants of our universe. Different configurations would lead to different physics, different particle masses, different force strengths, perhaps even different numbers of forces and particles. This leads to the string theory landscape, a vast number of possible universes, perhaps 10 to the power of 500 or more, each with different physical properties. Our universe would be just one valley in this vast landscape of possibilities. But why these particular laws and constants? This brings us to one of the deepest mysteries in cosmology, the fine-tuning problem. Many of the fundamental constants of nature appear to be exquisitely fine-tuned for the existence of complexity and life. If the strong nuclear force were just a few % stronger or weaker, stars couldn't form helium or would burn out too quickly. If the electromagnetic force were slightly different, chemistry as we know it would be impossible. If dark energy were much stronger, the universe would have expanded too quickly for galaxies to form. The anthropic principle offers one explanation: we observe these particular values because we couldn't exist in a universe with different values. In a multiverse with many different universes, we necessarily find ourselves in one compatible with our existence. It's like asking why Earth is at just the right distance from the Sun for liquid water. There might be billions of planets at different distances, but we evolved on the one that was suitable for life. But the anthropic principle feels unsatisfying to many scientists. It seems to give up on finding deeper explanations for why the constants have the values they do. Alternative explanations include the possibility that the constants aren't actually constant but evolved to their current values through some dynamical process, or that there's some deep mathematical principle we haven't discovered yet that requires these particular values. Dark matter remains one of the most frustrating mysteries in modern cosmology. We've known about its gravitational effects for nearly a century, since Fritz Zwicky observed that galaxies in clusters move too fast to be held together by the gravity of visible matter alone. Vera Rubin's observations of galaxy rotation curves in the 1970s confirmed that galaxies are surrounded by massive halos of invisible matter. Today, we have overwhelming evidence for dark matter from gravitational lensing, the cosmic microwave background, and large-scale structure formation. Yet we still don't know what dark matter is made of. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that interact through gravity and possibly the weak nuclear force but not electromagnetism, making them invisible. Experiments deep underground, shielded from cosmic rays, search for the rare occasions when a WIMP might collide with an atomic nucleus. So far, these searches have come up empty. Other possibilities include axions, extremely light particles proposed to solve a problem in quantum chromodynamics, primordial black holes formed in the early universe, or modifications to gravity itself that make it stronger on large scales than Einstein's theory predicts. Each possibility has its advocates and its problems. The failure to detect WIMPs has led many physicists to consider alternatives more seriously. Dark energy is even more mysterious. Discovered through observations of distant supernovae that appeared fainter than expected, indicating the universe's expansion is accelerating, dark energy seems to be a property of space itself. The simplest explanation is Einstein's cosmological constant, a fixed energy density of empty space. But when physicists try to calculate what this energy should be based on quantum field theory, they get an answer that's 10 to the power of 120 times too large, perhaps the worst prediction in the history of physics. This cosmological constant problem suggests we're missing something fundamental about the nature of space, time, and energy. Some theories propose that dark energy isn't constant but changes over time, driven by a field called quintessence. Others suggest that what we interpret as dark energy might be a sign that general relativity breaks down on cosmic scales, requiring a modified theory of gravity. The mystery of cosmic inflation also remains unsolved. While inflation elegantly explains many features of our universe, its large-scale uniformity, geometric flatness, and the absence of magnetic monopoles, we don't know what caused it. The inflaton field that drove inflation is hypothetical, and there are many different models of inflation, each making slightly different predictions. Some models predict that inflation should create gravitational waves that would leave a distinctive pattern in the cosmic microwave background, but these haven't been detected yet. Even more puzzling are anomalies in our observations that don't fit our standard models. The Hubble tension is one such mystery. Different methods of measuring the universe's expansion rate give different answers. Measurements based on the cosmic microwave background suggest the Hubble constant is about 67 km per second per megaparsec, while measurements using supernovae and other distance indicators give values around 73. This discrepancy might indicate new physics or systematic errors in our measurements. There are hints of other anomalies too. Some observations suggest the universe might not be perfectly uniform on the largest scales, challenging the cosmological principle that the universe looks the same in all directions. The cosmic microwave background shows some unexpected features, like the cold spot, a region that's unusually cold and empty. Galaxy clusters seem to be moving in coordinated flows, sometimes called dark flow, that might indicate structures beyond our observable universe. The question of consciousness and its place in the universe represents another deep mystery. How does matter organize itself into forms capable of subjective experience? Is consciousness fundamental to the universe, as some interpretations of quantum mechanics suggest, or is it an emergent property of complex information processing? The anthropic principle raises the possibility that consciousness might be necessary for the universe to exist in some sense, that observers are required to collapse quantum wave functions and create definite reality. Some physicists have proposed even more radical ideas. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. This might mean our three-dimensional universe is actually a projection of information encoded on a distant two-dimensional surface. Black hole physics supports this idea. The entropy of a black hole is proportional to its surface area, not its volume, suggesting that information is fundamentally two-dimensional. The simulation hypothesis proposes that our universe might be a computer simulation run by beings in a higher reality. If it becomes possible to create realistic universe simulations, and civilizations create many of them, then most conscious beings would exist in simulations rather than base reality. We might be living in one of these simulations, which could explain some of the universe's puzzling features, like the apparent fine-tuning of physical constants or the quantum nature of reality at small scales. Time itself presents profound mysteries. Why does time have a direction, flowing from past to future, when most laws of physics are time-reversible? The arrow of time seems connected to entropy and the second law of thermodynamics, but the deep relationship between time, entropy, and consciousness remains unclear. Some theories suggest time might be emergent rather than fundamental, arising from more basic timeless physics. The measurement problem in quantum mechanics hints at deep mysteries about the nature of reality. Quantum systems exist in superpositions of multiple states until measured, when they collapse into definite states. But what constitutes a measurement? Does consciousness play a special role, or does any interaction with the environment cause collapse? Different interpretations of quantum mechanics give different answers, from the many worlds interpretation where all possibilities occur in parallel universes, to objective collapse theories where wave function collapse is a real physical process. As we push our theories to extremes, to the first moments after the Big Bang, to the centers of black holes, to the far future of the universe, we encounter singularities where our mathematics breaks down. These might be signs that we need new physics, perhaps a theory of quantum gravity that unifies general relativity and quantum mechanics. Such a theory might reveal that space and time themselves are emergent from something more fundamental, just as temperature emerges from the motion of atoms. The mysteries extend beyond physics to the question of life itself. How did non-living chemistry become biology? Is life common in the universe or extraordinarily rare? The Fermi paradox highlights this mystery. If life is common and some civilizations develop advanced technology, why haven't we detected any signs of them? The Great Filter hypothesis suggests there might be some extremely difficult step in the development of intelligent life that few or no civilizations survive. As we contemplate these mysteries, we're reminded of how much we still don't know. Each answer we find reveals new questions, deeper mysteries. The universe continues to surprise us, to challenge our assumptions, to reveal new layers of complexity and beauty. Perhaps that's the most wonderful thing about our cosmic story. It's still being written, still full of mysteries to solve and wonders to discover. And so we reach the end of our journey through time and space, having traveled from the first quantum fluctuation that sparked existence itself to the cold, dark eternity that awaits in the far future. We've witnessed the birth of atoms, the ignition of the first stars, the assembly of galaxies, the forging of elements in stellar furnaces, the emergence of life from non-living matter, and the rise of consciousness that allows the universe to contemplate itself. What a magnificent story it has been. As you drift off to sleep tonight, consider that you are not separate from this cosmic tale but an integral part of it. Every atom in your body, save for hydrogen, was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces that blazed billions of years before Earth existed. You are, quite literally, made of star stuff, a collection of atoms that have been on an incredible journey through space and time to arrive at this moment, arranged in just such a way as to be you. The universe has spent 13.8 billion years preparing for this moment, your moment of existence. It took the Big Bang to create space and time, inflation to smooth and flatten the universe, the first stars to forge heavy elements, supernovae to scatter those elements through space, gravity to gather them into new stars and planets, chemistry to assemble them into increasingly complex molecules, evolution to organize them into living beings, and countless generations of your ancestors surviving and reproducing to finally produce you. When you look up at the night sky, you're not looking out at something separate from yourself. You're looking at your extended family, your cosmic ancestry. Those distant stars are your cousins, formed from the same primordial hydrogen, following the same physical laws, participating in the same cosmic story. The space between the stars isn't empty void but the medium through which you're connected to everything else, the fabric of spacetime that binds all existence into a single, unified whole. Consider too how remarkable it is that we've been able to piece together this story at all. We are arrangements of atoms that have developed the ability to understand atoms. We are products of evolution who have discovered evolution. We are consequences of physical laws who have deduced those very laws. The universe has evolved conscious beings capable of understanding their own origins, like a vast cosmic mind achieving self-awareness. Our knowledge of the cosmic story has all been gained within the last few centuries, a mere instant in cosmic time. Your great-great-grandparents had no idea that galaxies existed beyond our own, that the universe was expanding, that atoms were made of smaller particles, or that humans shared common ancestors with all life on Earth. In just a few human generations, we've gone from thinking Earth was the center of everything to understanding our true place in an vast, ancient, evolving cosmos. And yet, for all we've learned, we've barely scratched the surface. We don't know what dark matter is, despite it making up most of the matter in the universe. We don't understand dark energy, which dominates the universe's energy budget. We don't know if our universe is unique or one of many. We don't know how life began or if it exists elsewhere. We don't fully understand consciousness, time, or why the laws of physics are what they are. The universe still holds countless mysteries, waiting for future generations to uncover. Perhaps that's part of the beauty of our cosmic story, it's not finished. We're not reading a completed book but participating in an ongoing narrative. The universe continues to evolve, stars are still being born, planets are still forming, and somewhere, perhaps, life is emerging for the first time on an alien world. The future remains unwritten, full of possibilities we can barely imagine. On Earth, we stand at a unique moment in cosmic history. We are the first species on this planet capable of understanding our origins and contemplating our future. We have the power to destroy ourselves or to spread life throughout the cosmos. We can choose to be a brief, failed experiment in consciousness, or we can become the means by which the universe explores and understands itself more fully. The choices we make in the coming centuries will determine whether Earth life represents a dead end or a new chapter in the cosmic story. As you lay your head on your pillow tonight, remember that you are participating in something magnificent. You are the universe experiencing itself subjectively, a way for the cosmos to know itself. Your thoughts, dreams, and experiences are not separate from the cosmic story but are the latest chapter in it. When you love someone, the universe loves. When you experience beauty, the universe experiences beauty. When you seek to understand, the universe seeks to understand itself. The atoms in your right hand probably came from a different star than the atoms in your left hand. You are a confluence of countless cosmic streams, a temporary arrangement of ancient matter that has momentarily achieved the remarkable state we call life. One day, those atoms will return to the cosmic cycle, perhaps to become part of new stars, new planets, new life. But for now, for this brief, precious moment, they are you. Think about the extraordinary chain of events that had to occur for you to exist. If the Big Bang had been slightly different, if the fundamental constants had other values, if the first stars hadn't formed, if supernovae hadn't scattered heavy elements, if the solar system hadn't formed just so, if Earth hadn't been at just the right distance from the sun, if life hadn't emerged, if evolution had taken a different path, if any of your billions of ancestors had died before reproducing. Change any of these and you wouldn't be here. Your existence is so improbable that it borders on the miraculous. Yet here you are, against all odds, a conscious being in a vast cosmos, capable of love and wonder, able to appreciate beauty and seek truth. You carry within you the history of the universe, encoded in your atoms, written in your DNA, manifested in your consciousness. You are a way for the universe to experience awe at its own majesty, to feel gratitude for its own existence, to marvel at its own mystery. As sleep approaches and your consciousness begins to fade into dreams, let yourself feel connected to the grand cosmic story we've traced. From the quantum foam that preceded existence, through the violent birth of the universe, the patient assembly of matter into ever more complex forms, the stellar alchemy that created the elements, the delicate dance of gravity and chemistry that built planets, the remarkable emergence of life and consciousness, to this very moment as you lie in bed, you are part of an unbroken chain of cause and effect stretching back to the beginning of time. Tomorrow, when you wake, you'll continue your part in this story. Every choice you make, every action you take, every thought you think adds to the cosmic narrative. You are not a passive observer but an active participant in the universe's ongoing evolution. Through you, the universe continues its journey of self-discovery, pushing forward into an unknown but undoubtedly remarkable future. So rest now, knowing that you are exactly where you belong, a precious and irreplaceable part of the cosmic story. Let your mind drift among the stars, your thoughts merge with the cosmic web, your dreams dance with distant galaxies. You are the universe dreaming of itself, and what beautiful dreams they are. Sleep well, cosmic traveler. Tomorrow, the story continues, and you'll be there to help write it. For now, let the vast peace of the cosmos fill you, the slow rhythm of celestial mechanics lull you, the ancient starlight that has traveled millions of years to reach your eyes tonight whisper you to sleep. You are home in the universe, and the universe is home in you. Sweet dreams, and thank you for joining me on this incredible journey through space, time, and existence itself. The story of the universe is your story, my story, our story, the greatest STO.